Okay, so we'll talk now about the calculations related to the mixture of gases of different or mixture of different gases or different compounds. For instance, in this example here, we have a mixture of 20 moles of oxygen, 30 moles of nitrogen, 15 moles of hydrogen, and 35 moles of methane. Um, and when dealing with gases, one important thing is to know the kind of concentration or the percent of each one of these components in the mixture. And we can calculate something what we call the mole fraction. And it's clear from the name that it is related to the moles. And this is the fraction, which is the ratio between the number of moles of the component by the number of moles of the mixture. So if I add them, all of them, it's 20 plus 30 plus 15 plus 35 is going to give 100. So if I want to calculate the mole fraction of a component, which is going to be Y of, for instance, O2, which is going to be the number of moles of oxygen divided by the total number of moles of the mixture, which is going to be 0.2. The same for nitrogen is going to be 30 divided by 100, it's going to be 0.3, hydrogen 15 by 100, and methane is 35 by 100, which is going to be 0.35. Um, so it's kind of easy to calculate, and it's a simple thing, and we need to, or it's needless to say that the summation of y I equals 1. If you add this, and this, the summation should be 1, because it's summation of fractions, which should be 1. Um, in case of dealing with a mixture of different solutions or different gases, for instance, this mixture, it's composed of 4 different gases, and you want to calculate the density of this mixture. The density equals Pm over RT according to this equation here. So I have P, I know the pressure, I know the temperature, I know R. They don't depend on the number of components, but this, how can I substitute in M? It says Pm over RT, and I have these components here, and I need to find which molecular weight. Should I substitute with the molecular weight of oxygen or nitrogen or hydrogen or methane? If I might say that I would put the molecular weight of the component that is present more than others, so, or present the most. So I have methane here, it's in 35%, while the others are less than that, so I can put the methane, but this is not right. I could put something or a molecular weight of any one of them. No, I have to put something that represents all of them. So to put the molecular weight that represents them, I put what I call the average molecular weight, which is the m bar. And the average molecular weight is calculated according to this equation. It is summation of the mole fraction multiplied by the molecular weight of each component. So for instance here, I want to calculate the average molecular weight of this mixture, so I multiply the 0.2 by the 32, which is of oxygen, and add it to 0.3 multiplied by 28, which is the molecular weight of nitrogen, and then add 15%, 0.15 by 2, which is the molecular weight of hydrogen, and 0.35 by 16, which is the molecular weight of methane, and I'll get the molecular weight that represents the average of all of these compounds. So this is how we do the calculations of the average molecular weight. For Dalton's law of partial pressure, this is something that we kind of visited last year in the chemistry course, but again, it is a law that is used to calculate the partial pressure of a component. And to understand the partial pressure of a component, we can say that if I have a mixture of 4, 5, 10, 100 components, then the total pressure of the components is considered to be the summation of partial pressures of the component. For instance, I have a mixture of these 4 components, like oxygen, nitrogen, hydrogen, and methane. And I have, where did it go? Yeah, here. So I have the 4 components, and I want to calculate the, or I know that they all are at like 2 atmosphere, 10 atmosphere, for instance, 10 atmosphere. So the 10 atmosphere are not only for oxygen, not only for nitrogen, not only for hydrogen, not only for methane, it's for all of them. But I can say that these 10 atmospheres are split to the pressure of oxygen and the pressure of nitrogen and the pressure of hydrogen and the pressure of methane. And this is what the Dalton's law says. It is says that the partial pressure of a component is the pressure, and this is an important definition. So please pay attention to it. It's the pressure of that gas if it alone occupied the entire volume of the original mixture at the same temperature. So if I assume that all other gases are not present and this gas is only present in the container, then the pressure in of this gas would be equal to its partial pressure in the mixture. Um, so I would say the Pi, the small p, is the partial pressure of component I multiplied by V equals Ni multiplied by R multiplied by T. Um, and the partial pressure is proportional to the mole fraction. So the pressure of a mixture of gases equal the sum of partial pressure of all the components. So the total pressure or the partial pressure equal the mole fraction multiplied by the total pressure. And if I add all the partial pressures, they're going to give me the total pressure of a gas. This is all for the gases now. I'm gonna stop now, and in case you feel that you don't understand them well, we will have some practice questions that we're gonna solve some problems to get this more clear. So we'll go to this later. Goodbye.